Okay, the next thing we're going to do in section 5.2, exponential functions, is we're going to take a look at the graph of the exponential function. And there's actually two graphs depending on the value of b, and we'll see why in a minute. So for values of b greater than 0, we're going to have one kind of graph. For values of b between 0 and 1, the graph will change. Let's take a look at why. I have some coordinate systems here. We'll put 0. Regardless of the value of b, again, anything to the 0 power equals 1. So the first thing we can note is, and let's do that down here. This is for any exponential function. So that is the point x equals 0, y equals 1. Again, that's a y-intercept. Whenever x equals 0, where are we on the y-axis? So regardless of the situation, we're going to be at 1. Let me go 2 squares for each unit. So that would be the value 1. Okay, so we know that. Another thing we know, regardless of the value of b, is you can never get the function to equal 0, because if I have a non-zero number, it's got to be greater than 0, and I raise it to any power, it can never become 0. Okay? So, second point for any exponential function, we have an asymptote. At the x-axis. In other words, y can never be 0. The function can never be 0, which means we can never be on the x-axis. We got to be above it. Okay. What makes the graphs different? Let's take a look at a number greater than 1. Let's say 10. When I raise 10 to a power, let's just start with 1. As the power increases, let's go say 10 to the 4th. As the power, or as x, increases, what's happening to the function? It's also increasing. F of x is increasing. So, as x approaches infinity, as it continues on and on and on, what does the function do? As x goes to infinity, the function is getting bigger and bigger and bigger. So the function also tends to infinity. Now, we know what happens at 0. It always equals 1. So now we're here. So if I start here, I know that every time I move in the x direction, I'm getting bigger and bigger and bigger by quite a bit. And what's happening is, if you plot actual points, you start to get an exponential curve like this. So I think we can already figure out what's going on here. The curve has to continue this way, and it has to get close to the x-axis but never touch it. So it looks like as we move this way, as we move in a negative direction, so let's look at this real quick. As x, yeah, we don't need to do that. We already have it. Okay, so again, x goes to infinity, the function goes to infinity. But what happens as x goes to negative infinity? It's getting smaller and smaller. Well, let's look at that. Let's start with, there's a minus power for x. Now let's get smaller and smaller. So x to minus 2 is minus 2 smaller than minus 1. So we're moving towards the left in the negative infinity direction. Let's look at this one. Okay, now to evaluate these, we just use our rule from last time. To turn a negative exponent into a positive, just move it to the other side of the fractions. So this would be 1/10, this would be 1/100th, this would be 1/10,000th, and so on. So you can see what's happening. As x approaches negative infinity, the function is approaching zero, but it will never get there, so it becomes asymptotic, the x-axis. So we'll get closer and closer, but never get there. All right, that's b greater than 1. If we're between 0 and 1, that means b is a number less than 1, but greater than 0, of course. When you have a number less than 1, it's kind of the reverse of this. So we're actually going to start off with numbers like, say, 1/10. That's less than 1. Whenever you raise a number that's less than 1, and again, and greater than 0, to a power, positive power here, you're going to get smaller and smaller. So you can see here, as x gets bigger, as x approaches infinity, what's happening to y? It's getting smaller and smaller. It's getting closer and closer to 0. So as x approaches infinity, the function, or y, however you want to write it, approaches 0. Again, doesn't matter what b is at the 0 power, it's always 1. So now we're starting at 1, but as we move out on x, we're actually getting smaller and smaller on the y values. So we're coming down like this. And again, you can see that x is still an asymptote. We'll never touch it. What happens on the other side? Well, the reverse of what we did here. If these powers are negatives, so now we're looking at x values out here. And let me just put a couple of them in here. Again, our rule from last time, if I want to turn this into a positive, I take the reciprocal, or I move everything to the other side of the fraction bar. So that'd be 10 over 1, or just 10 to the 1. This would be 10 over 1, or 10, instead of minus 3, now becomes a 3. And you can see what's happening. As x gets smaller and smaller negatively, the function's getting larger and larger. So as x approaches negative infinity, so we're moving this way, the function's just getting bigger and bigger. The function is approaching positive infinity. So it looks like this. So there's your exponential function graphs. Again, it's the same function, but there's a difference in the direction. So these apply to all exponential functions. Something else that applies to all of them, look at the domain. The domain is any x value you want. Doesn't matter what b is. So the domain is always minus infinity to plus infinity. And then the range, again, regardless of what b is, starts just above 0 and goes to infinity. So the range looks like this. Okay, differences. Again, b is greater than 0. We've got an increasing function. In other words, any 2 points I pick, the point to the right on the greater the x value, the greater the function value. So any 2 points, the point to the right of it creates a bigger function value, so that's increasing. And the opposite of that, in this situation, we have a decreasing function. And then finally, these will be named a lot of times, particularly in word problems. An exponential function like this, where it's increasing, b is greater than 1, this is generally referred to as growth, exponential growth. So let me write that. Exponential growth. And we'll be using these kind of functions later for stuff like population growth, growth of a germ population, that type of stuff. A lot of those populations follow an exponential growth curve. When you have something decreasing, that's a lot of times referred to as exponential decay. And exponential decay equations fit well with stuff like radioactive half-life. As time goes on, the radioactive particles decrease exponentially. And this can be used for other kinds of decay problems, like for instance carbon-14. We'll probably run into an example or a homework problem of that, where the carbon-14 molecule disintegrates over time at a certain rate, and that's a decreasing situation, so it's an exponential decay. All right, I want to look at one more thing now, and then next time we'll actually probably solve some problems with this. What I've got here, let's read this. What I've got here is a function that we want to go back to chapter 3 on, and I'm not sure if chapter 3 called out the exponential function or not, but if you look at this, it's a function and we would like to graph it. We can apply the toolbox tools that we used in chapter 3. By first looking at this and realizing it looks a lot like this, it's an exponential function. A couple of things. Number one, that's going to be the basic function, then we're going to modify it here. Also, b is greater than 2, so we know that it's going to go up. Also, we know right now it goes through the point 1, so let's go again. We'll make every second one 1. Okay. What I'm doing here is just getting an idea of what the starting family looks like. It's an exponential function. It's increasing, so we can just kind of sketch that. We don't care a whole lot about what's going on yet. So we got this situation. We know it's asymptote. That's an asymptote right there. Okay, we know all that from what we just saw on the previous page when we looked at the basic graph. Okay, now what we want to do is graph this equation here. So again, if you remember from chapter 3, when you're dealing with asymptotes, generally you want to move those first. So if you look at this equation, we're going to go to the left 2. Whoops, let me go this way. We're going to go to the left 2, and we're going to go down 1. That's what these transforms do. Okay, since this is a horizontal asymptote, it can only move up and down. So we're going to take a look at this, and we're going to move the asymptote down 1 unit. So there's our new asymptote. Okay, so we're going to come down to that somehow. All right, this point right here was our original y-intercept, which again from the last page is 0, 1. And what we're doing here is we're going to go to the left 2, so we're going to take this 0 and go 2 to the left, so we minus 2 from that. And then this 1, we're going to come down 1, so we're going to subtract 1 from that. So that's our new intercept point. So that would be here, and 1, 2 would be here. Let me extend this a bit. Okay, so we got a graph that's coming through like this. And then the last thing you want to do, and it's an easy thing to do, but to get a more accurate picture of where this thing's going, because I don't know, it's kind of hard to just sketch it over to that y-axis. Find the new y-intercept here, okay? Because we had a y-intercept, but it moved away and actually became an x-intercept. So now I need a y-intercept. Well, again, what is a y-intercept? Evaluate the function at 0. So here we are. Put a 0 in for x. Okay, 2 squared is 4. 4 minus 1 is 3. So if I go up 3, 1, 2, 3, right here, I need to go through the axis at that point. So it just helps to get a more accurate sketch here. All right, so that's how we can sketch these kinds of equations, starting from our basic knowledge of what an exponential function's graph looks like. Okay, that's it.